Hello grade 11 GED 2019-2020 students. Still we are in topic 4, electric fields. This is lesson 4.4. We are going to do lesson 4.4 before 4.3. Okay, uniform electric fields. The objectives for this lesson are to calculate the field strength of a uniform field, to calculate the force on a charge in a uniform electric field, then to describe the effect of a uniform electric field on the motion of a charged particle. Okay, let's start. What do we mean by uniform electric field? The concept indicates that we have the same electric field, E. So, for a uniform electric field, the value for E at any point in that field and also the direction will be constant. So, E will have only will have a certain value and direction at any point in that field. To get a uniform electric field, as we mentioned before, we should have here two parallel plates with different charges. So in a lab, if we have a high voltage power supply, one plate will be connected to the negative potential, the other to the positive potential. So we have a negative plate, charge plate, and a positive charge plate. And here, as we know, that the direction of E will be from the positive to the negative. The lines are parallel here, and E, the electric field here, said to be uniform. So we have uniform field. At any point here, for example, we have the same value and direction of the electric field. The strength of the uniform field is given by E equal to V over D. So this is the strength of the electric field. We call it sometimes electric field just for simplicity. This is the potential difference between these two plates. So potential difference, or the voltage that we have here, and D is the separation between these two plates here, D. So V is in a unit of volt, D is meter, so you will get for E volt per meter as a unit. As you see here, that the voltage is directly proportional here from this formula, that the voltage is directly proportional, E the field strength is directly proportional to the voltage, and it is inversely proportional to D. This means that the voltage, the higher the voltage, the stronger the field. Higher the voltage, stronger the field. But The greater the separation, the weaker the field. They are inversely proportional to each other. Okay. Now let's do this question. We have here two parallel plates are shown separated by 25 centimeters. This is the separation between the plates. Let us write our given quantities. Our D equal to 25 centimeters, and we should here convert it to the SI unit meter by dividing by 100 or multiplying it 10 times 10 to the minus 2. So 25 divided by 100, it will be 0.25 meters. Okay, copy the diagram and draw the feed line. Draw the feed to represent the field between the plates. Now you see here plate B, it has positive 2 kilovolt as potential. So this is positive. It is connected to the positive terminal of our power supply, and this is a plate which is earthed, and when the plate earthed, so it should have 0 volt, and this plate will become negative with respect to plate B. It has less potential. So you know that the field lines direct from the positive to the negative, and this is giving us the direction for E, electric field. Now what is the potential difference between points A and B? This is point A and this is point B. So point B is on the plate, the positive plate, so it should have the potential of positive 2 kilovolt. So the potential here at B is 2 kilovolt. So the potential, this is part B, the potential at B is 2 kilovolt, and we can convert kilovolt to volts by multiplying 10 to the 3 or 1000. So 2 kilovolt should have 2 times 10 to the 3 or 2000 volts. This is the potential for B. Potential for A, VA, is 0. So VA is 0. What will be the difference? Potential difference will be VB minus VA, which is equal to 2 times 10 to the 3 volts or 2000 volts. Part C, what is the electric field strength? So they are asking about E. Between points A and B, between these 2 points. So we have the separation and we have the potential difference. We will apply E equal to V over D, and we have the potential difference between plate A and B, which is this 2000, and this is in volts. Let's write the units just to get the unit for E, and our D is 25 centimeter and we convert it to meter, so it's 0.25 meters. This will give us the value for E, which is 8000 volt per meter. Okay, in part D, calculate the electric force So they need what? Force. The electric force on a charge, you know, any charge here in the field should be affected by a force, which is electric force. And we know that the electric force equal to, we know E equal to force divided by charge. So this will give us that the force equal to E multiplied by Q, the charge. So here the electric force on a charge of, this is our charge, so our value is 5 microcoulomb. We will convert it to coulomb, so 5 times 10 to the minus 6 coulomb. So they are asking us if a charge is at point here C, this is the amount of charge, what should be the electric force and in which direction does the force act? To calculate the force here, we have this charge if has been placed at any point, as far as the charge is constant and E is constant, so it will affect by the same force. So the force on this charge will be the same at C, D, or any point here, because we have uniform E. So to get F, we have E, which is this 8,000 multiplied by Q, this is our Q, 5 times 10 to the minus 6, and this will give us the value for F, which is 0.04 newtons. What is the direction of the force here? So for the charge, for the positive charge, which has been placed here at C, where should be the direction here of the force? It is a positive charge, so it should attract to the negative plate. Yes? So this is the direction of the force. You see, it is with the same direction of E. Again, positive charge should be attracted to the negative plate. So the direction for the force is towards left, or plate A, or point A. So to the left. Now this is again the force on a charge moving parallel to a uniform electric field. Just now we have seen the example, the question before. We have electric field to the left, so this means it's going from positive to negative. Okay, so this is our plate here, which has positive charge. Here we have a plate which has a negative charge. Two plates are parallel to each other, so a uniform electric field will form between them. The direction for the electric field, as we know, is from positive to negative. This is the direction for the electric field. So as you know, if at this point, any point here, we put a positive charge, the positive charge will move towards the negative plate. So this will be here the direction for the electric force. with the same direction of electric field. Electric field from positive to negative, and the force acting on this charge will be towards the negative because this is a positive charge. But what if we have, okay, if we have a negative charge? So if we place a negative charge here, if we place a negative charge here at this point, for example, negative charge will attract to the positive plate. So the force for the negative charge will be opposite to the direction of E, as you see. Why? Because this is the direction for E is from positive to negative, and the negative charge should move towards the positive plate. So this will be the force acting on a negative charge, which is opposite to E. And of course, we know at any point F equal to EQ. So if we have the same charge and this is uniform, so F is constant at any point. That give us, there is as far as, okay, we have here an electric force, then this charge should have an acceleration. A equal to F divided by M. This is from Newton's second law. So the charge should accelerate here, the positive charge accelerating towards the negative plate, the negative charge accelerating towards the positive plate. And this acceleration is the force divided by the mass of the particle or the charge. Okay, now question 2. Two parallel metal plates separated by 2 centimeters. So we have 2 parallel metal plates separated by, this is D, 2 centimeters, so it is divided by 100.02 meters. Have a potential difference of 5 kilovolts. So V between 2 plates is 5 kilovolts, and we know if we are going to convert it to volt, multiply it by 1000 or 10 to the 3, so 5 times 1000 will give us 5000 volt. We are converting from kilovolt to volt, so multiply by 1000. Calculate the electric force acting on a dust particle between the plates. If there is a particle here and with a charge of 8 times 10 to the minus 19 coulomb, and this is SI unit, no need to convert it. So there is a particle here with a positive charge, and you know that this particle will so if you have, for example, this is a positive and this is a negative, and so this particle is positive, it will move towards the negative direction. This is the direction of the force, and it is the same direction of E, from positive to negative. And this is positive charge, so the force will be towards the negative plate. So they need the force acting on this particle. Again, force equal to from, we know that E, uniform E, is equal to F divided by charge. So our F is E times Q. But where is our E here? We have to calculate it. First, we have to calculate E from V over D. So we have our V, 5,000, and our D is 0.02, and this is going to give us 2.5 times 10 to the 5 volt per meter. It can also have the unit of Newton per coulomb from here. So the unit of E can be Newton per coulomb, and it is the same as volt per meter. So let's substitute the value of E here in this equation. So we have 2.5 times 10 to the 5, and our Q is here 8 times 10 to the minus 19, and this is going to give us 2 times 10 to the minus 13 Newton. We are calculating F. Here, the force on a charge moving initially at a right angle to an electric field. Now we have two parallel plates, a negative and positive, and as we know that E is from positive to negative. Here, from positive to negative, towards up. This is the direction of our electric field. An electron is entering to the right. So the electron entering to the right, so initially it was perpendicular to the direction of electric field. But in the previous example, the electron was moving, or the charge was moving parallel to the direction of the electric field. Here we are initially the particle is perpendicular to the direction of the electric field. What will happen here? When the electron enters here, the field, it will be affected by a force, which is the electric force. This is the electric field strength, and this is the charge for this particle, electron. Where will be the direction of this force? As you know that electrons have negative charge, so they will be attracted to the positive plate. So the force will be downward, as it's illustrated here in this figure. So the force is down here towards the positive. This will make the particle follow this projectile path. And this is very similar to the projectile motion. If you have, for example, here a ball and with an initial velocity v here, and for a projectile motion it will follow this trajectory. This is a parabolic path. Why this is? As here, because the gravity downward, so and there is no acceleration, horizontal acceleration. So what will happen here, the horizontal v will be constant, Vx. Yes, but the vertical velocity, the vertical component of the velocity, here no vertical component, but when it's coming down, it will start due to the gravitational acceleration and will increase downward. So it is the same here. For this particle, the gravitational acceleration can be negligible, and we are only dealing with the acceleration due to the electric force. So due to this acceleration, okay, it will follow this path. The force is downward, and it is the same everywhere here because we have the same E and the same Q. The velocity, the horizontal velocity, is constant at any point, but it is accelerating downward. This is for the force if the charge initially entering an uniform electric field perpendicularly. Let's do a question. A proton, and we know that proton has a positive charge, is it's moving between two charged parallel plates. So this is the upper, which is positive, and this is the lower, which has negative charge. The charge on the proton, this is the charge, and this is given with SI units. So we have the charge on the proton 1.6 times 10 to the minus 19 coulomb. Now here we have the D here, 2.5 centimeter. So our D 2.5 centimeters, and as usual divided by 100, it will give us 0.025 meters. Now, or 2.5 times 10 to the minus 2, the same. This means that we are dividing by 100. Now copy and draw the electric field between parallel plates as usual. Electric field from positive to negative. This is the direction of the electric field. Now, in which direction does the force on the proton act when it is in position B? Here B, the proton already entered the electric field, and this is a proton with a positive charge, so it will be affected by a force downward, and it's very clear that it is moving towards the lower plate. So this means that the force is down. So here it is the direction of the force. And that was the direction of E. So in which direction the force, okay, act? Down, towards the negative plate. And again, because of this force, the particle, the proton, is accelerating downward, and it will follow this parabolic path, this trajectory. Okay, Now at any point here, at any point, it is very important to know, as we mentioned, that if it is entering with a velocity v horizontal, so the horizontal component of the velocity vx is constant, no any x force in the horizontal direction, but there is a force downward. That's why the velocity, the vertical component of the velocity will increase as it's going from B to C. Okay? At any point here, the resultant velocity will be tangent to that, a tangent to the path at that point. So it has, this is when it's outside, no magnetic field. Let's only be inside. For any point here, at any point, the horizontal V is constant and the vertical V downward is increasing, and V inside, or at any point, at V at any point, should, how to determine the direction of B at any point, V at any point, we should take the tangent to the curve at that point. This is the resultant V. Now what will be the magnitude of the force on the proton when it's at C here? And as we know that the magnitude of the force is constant anywhere between inside the electric field. So for C, part C, the electric force, the force is equal to E times Q. Again, we don't have our E, we have to calculate it, which is now to get V, and because the force here, this is the value of the force. Sorry, we have the value of the force. It's given. This is the value of the force at position B, and it should be, as we mentioned, the same value at point C. As we know, force equal to E times Q, and E is constant. It's the same particles, so the force at any point the same. Force at B is given as 6.4, so also at C it will be 6.4 times 10 to the minus 14 N. Okay? No calculations here. For part D, calculate the electric field strength between the plates. So, we are asked to calculate E. So for the E, we know that E equal to F divided by Q, and we have our F 6.4, times 10 to the minus 14. This is the electric force at any point inside, and our Q is the proton, and we have the charge of proton 1.6 times 10 to the minus 19, and this will give us the electric field strength, which is 4 times 10 to the 5. It can be Newton per coulomb. Now for part E, calculate the potential difference between the plates. We know that V equal to, from V equal to, E equal to V over D, so our V equal to E times D. E times D. So we have our E, 4 times 10 to the 5, this is our E. and our D is this here, the separation. We already converted 0.025 meter, and this is going to give us 1 times 10 to the 4 volt, 10,000 volt. Okay, now this was the end of our lesson for today. Thank you.